And welcome, Dan Jeske.
Hi, everyone.
All right. Great. Okay, so I hope everyone had a chance to grab a drink or something. So before our first keynote talk, I'd like to take a few minutes to introduce the speaker, Dr. Daniel Jeske, to all of you. Dr. Daniel Jeske is professor and vice provost of academic personnel at University of California, Riverside. He has had distinguished careers in industry, academia, and government. He began his career at AT&T Bell Laboratories after finishing his MS and PhD degrees in statistics at Iowa State University. In the Bell Lab, he was a distinguished member of technical staff and moved to leadership as a technical manager. While he was at Bell Lab, he was a part-time lecturer in the Department of Statistics at Rutgers University. In academia, he is an elected fellow of the American Statistical Association, ASA, and an elected member of International Statistical Institute, ISI. He is also elected member of the Board of Trustees of the National Institute of Statistical Sciences, NISS. His primary research interests include statistical process control, classification methodologies, reliability modeling, engineering applications, and biostatistics applications. His research has been supported by grants from DHS, NIH, NSF, and some California agencies. In the past, he served as associate editor of Technometrics for 3 years. He was editor-in-chief of the American Statistician. He's currently an associate editor of Applied Stochastic Models in Business and Industry. Over the years, Dan has taken on numerous leadership roles, including 7 years as chair of UCR Department of Statistics, 14 years as director of UCR Statistical Consulting Laboratory. He was member of ASA Board of Directors, vice chair of ASA Council of Chapters Governing Board. He was a president of Southern California chapter of the ASA. He is currently president of the International Society for Statistics in Business and Industry, ISBIS. In the government sector, Dan has had extensive consulting experiences for the Mathematical Analysis Research Corporation, MARC, a subcontractor to the U.S. Navy. Due to the time constraint, this short intro only includes some highlights of Dan's achievements and leadership. Without any delay, please welcome Professor Dan Jeske.
Thank you so much, PMU, for that and for the opportunity to participate in this Graduate Student Network conference of NISS. I'm glad to be back in an event with my friends at NISS, many friends at NISS. I do appreciate the roles that I've been able to help them with, and was really glad to see this conference burst onto the scene, I think maybe 2 or 3 years ago. And the attendance here today is wonderful. And so are the talks. I'm really quite impressed with the complexity of the problems that you are all probably working on, and certainly the ones I've heard speak about today. And doing so with the modern methodologies. It looks like as educators in the field, we've really brought in some of the new ideas and some of the new statistics. Data science is one example to what we're training our next generation statisticians to be. So it's really healthy time for our field. I'm going to offer you a little bit more of a casual talk as we slide into the afternoon portion of the first day here. But also maybe have some modern things in, and particularly the text mining aspect of classification. That's going to be the sort of the second half of my talk after I introduce something about classification that I've worked on for a few years, which is neutral zones. I want to tell you about those first, and then get to the new application, which is around text classification. Okay, so first, a little background on statistical classification. Basically, the idea with that is we have a set of features represented by vector X that are measured on an object. And there's a statistic that we calculate from those features, it's a real number. So we map those features, and maybe just to make it concrete, it might be like somebody's blood pressure, somebody's heart rate, somebody's weight, and so on and so forth. And we come up with a function t that maps those features, and there might be a lot of them. Could be high dimensional statistics, right? If we have many features on an object, and we map them into a function that transforms them into a real number r. And then, depending on the magnitude of that number, if it's bigger than some threshold, which I'm representing here by the constant u, we would classify that person into a class identified by 1. So I'm laying the groundwork here for a 2-class classification setting. So maybe it's like a patient is either sick or they're not, right? And if that transformed statistic from all their features is bigger than some number u, we're going to make a prediction, statistical prediction, that they're sick. So that maps to saying that the predicted class is class 1. Otherwise, if it's less than u, we'll say probably they're not sick. And obviously you can see how this has applications to medical diagnostics. All right, so then a little bit of notation here, because as we try to understand the properties of this statistical classifier, we need to contemplate what the distribution of t of x is. This is our random variable. As patients come into the clinic and we measure their features and we calculate their statistic t, it's random, right? Because we have many patients with many different sets of features. And it's important to identify the conditional distribution of that statistic given class 0. So sticking with our medical example, what's the distribution of t for non-diseased patients? That would be c equals 0, non-diseased. And then all those non-diseased patients are going to manifest in some value of t, and there'll be a distribution for those values of t for non-diseased patients, and we represent that by capital F. And correspondingly for the diseased patients, which are class equals 1, there'll be another distribution for the values of t, and that's called G. Now, this is classic terminology here for classifiers. That's why I called this section like fundamentals of statistical classification. There are important metrics, and they're generically sort of described as ROC metrics. ROC is an acronym for Receiver Operating Characteristics. It really doesn't mean too much. Those 3 words together, Receiver Operating Characteristic, unless you're an engineer. And I learned this when I was at Bell Labs, that this is a very important acronym in engineering when it comes to signal processing. I don't really think it means so much for statistical classifiers, other than the fact that a plot that we draw resembles the same plot that those engineers draw. But I don't think you have to worry too much about like, why is it called ROC? It just is. But the metrics themselves are very intuitively important. And here they are. So one is called the false positive rate of a classifier. And remember, the classifier is indexed by this threshold u, right? So whatever you choose for u changes the properties of the classifier for sure. And the false positive rate of a classifier is just going to be the probability you make a mistake and you say a non-diseased patient is diseased, right? We obviously, we don't want to be doing that too often. But you can see based on the distribution of t given c equals 0, that's just going to be 1 minus f of u, right? Because the probability c hat equals 1 is the probability that t of x is greater than or equal to u. And if we're computing that probability conditional on c equals 0, the conditional distribution is f. So we get this relationship between the false positive rate of a classifier and this underlying distribution for t, conditional distribution. Well, the other mistake we can make in a 2-class setting is a false negative rate. And that's when we have a diseased patient and we predict them to be non-diseased. And that's just going to be now the probability that t is less than u, because that's how we get c equals 0, c hat equals 0. And then you can see then we're using the distribution G. False negative rate can be a very serious mistake in medical applications, right? Because if you send a patient home who's sick because your classifier said they weren't, they're not going to get any better, and they are likely going to maybe get worse. So we really have to be careful in medical diagnostics with this false negative rate. False positive rate, not great either, but what's going to probably happen if you mistakenly classify a non-diseased patient as diseased, you'll start to do some other tests, and you'll probably discover somewhere along the line that maybe they're not really sick after all. So the consequence there is just raising alarm in the patient for a week or two or a month. So you don't really want to do that, but certainly the false negative rate in medical applications can be a much more severe error. So that brings out the point here that controlling these two conditional error rates, false positive and false negative, is really a good goal to have, rather than maybe only thinking about the overall error rate. And we'll talk a little bit more about that in a minute. Then two other metrics that are related are sensitivity and specificity. And these are just computed from the false negative rate and the false positive rate. We want both FPR and FNR to be small. Therefore, we want both sensitivity and specificity to be large, right? That's kind of like the only maybe reason to be talking about sensitivity and specificity instead of false positive rate and false negative rate. They're basically an equivalent pair of metrics. All right. Okay, so next is this curve. So this is a curve that engineers, as I mentioned, draw a lot when they're doing signal processing. But this is a curve that we also draw for classifiers that helps us think about the trade-off between this threshold U and what we would get for sensitivity and specificity, or equivalently FNR and FPR, right? Because it's a plot of sensitivity versus 1 minus specificity. So now we have to kind of do the math in our head again. We want both of these to be large, right? Sensitivity and specificity. But if you plot 1 minus specificity, then you want that to be small again, because after all, 1 minus specificity is just false positive rate. So I could have just labeled this one false positive rate instead of 1 minus specificity, right? So then, well, how do we get this curve, this solid curve? Well, we just run through different values of U and then calculate for that choice what the sensitivity and specificity are. And each time we change U, we get another point on this curve. So we're tracing out a locus of points by running through different choices of U. And so it's kind of like a parametric function, right? It's like, you know, you have like x of t, y of t, and then you let t vary, and you get all the points that are the locus of the points. That's exactly what a ROC curve is. And we know that choices of U that push us up to this upper left corner are the ones that we have high sensitivity and low 1 minus specificity, and that's good because 1 minus specificity is false positive, right? So we want low on the x-axis and high on the y-axis. We'd love to be up here in this region of the curve. And you're generally going to always get a bow-shaped, this dashed line is just the 45-degree line. So you're generally always going to get a curve that pushes up to this upper left corner. And the better classifiers, the ones that have the most potential to be useful, are the ones that have their bow very sharp and kind of climbing up into that upper left corner. If it's a very weak bow, then there isn't a lot of potential for that classifier to be useful. And in fact, another metric that I haven't mentioned here is the area under the ROC curve. That's all this area under the black curve, all the way down to the x-axis here. That is a summary statistic of the potential for a classifier. So these are the basics. And now I want to talk about how that ROC curve is used. And because now you have a picture of all the possible choices of U that you might think about, and now you have to pick one, right? You have to basically to define the classifier, you have to lock in on a particular value of U. But this curve helps you do that. And because it shows you the trade-off between if I pick a U down here, what's my sensitivity and my false positive rate? Remember, this 1 minus SPU is false positive rate. Or if I pick one over here, you know, I can see that trade-off. And you play this trade-off game to come up with what you think you're comfortable with for U. This is the classic way of building a classifier. And one sort of classic threshold is called the Youden threshold. And it's the choice of U that minimizes the sum of these two false positive rates and false negative rates. And that turns out geometrically to be the same point that gives you the maximum vertical distance between the reference line and the bowed curve, as I'm showing here. If you look at that, you'd probably agree that that red line is certainly longer than if I drew it down here. And I don't know, maybe it could be here, but the idea is there is a place where this vertical red line would be the biggest, and then where it touches this bowed curve, that's the value of U that we would use to define our classifier. That's how that works. There are other ways to choose a threshold from this ROC curve. One way, because we know we'd love to be up here, right? So you could measure the distance from this point, 0, 1, to the ROC curve, and all the possible points on it, and find the point that has the closest to this upper left corner. Okay, so now we come to this neutral zone concept. So this is a couple papers down here show some development of adding neutral zones and using them in some applications. And the idea is really simple, but as sometimes simple ideas are effective in terms of making a practical impact. This isn't really that deep of an idea, honestly. It's a simple idea to, instead of forcing us to use one threshold from the ROC curve, we're just going to choose two. So here's that same ROC curve in a generic sort of setting. But now, instead of like picking the Youden threshold and saying our classifier is based on this formula, where I just say 1 if I'm bigger than U and 0 otherwise, I'm now going to choose two thresholds, U1 and U0, and I define my classifier like this over here in the yellow, where now I'll still say 1 if T is big enough, but now before I say 0, I want it to be small enough. And then anything in between, I'm going to say I'm neutral about. I don't know. So this is recognizing when there's too much ambiguity about the features to confidently place it into class 1 or class 0. And this is really especially what we want to do. You can see some of my work here is in the medical research journals. This is really what we want to do with medical diagnostics, right? We want to only make classifications about someone being diseased or non-diseased when we're really sure or highly sure that we're making the correct decision. Because if it's borderline, we don't want to just arbitrarily say, well, we got to make a decision. So let's look for the shred of evidence that we think is there, although weak. There's a shred of evidence that maybe they are diseased or maybe they're not diseased. We're going to just call them one or the other, right? No, I don't think we want to do that. We want to recognize that that's too close of a call for the set of features we have. And that'll be reflected in a statistic that's in between the values that give us confidence. So let's call this classification outcome neutral and set that person aside for follow-up, additional tests, measure more things that might be more expensive than you wish to measure on everyone. But now we have someone that the inexpensive features weren't good enough to tell us what we need to know with confidence. So we recognize that by classifying them as N for neutral, and then we will refer them to additional follow-up where we might do a little bit more invasive testing, a little bit more expensive testing, maybe a little bit more uncomfortable testing, right? You know, there are procedures that could be thought of as screening procedures and are light and easy and work for many, many people. But then sometimes there are cases where you need to escalate what you try to figure out about someone. Yeah. So we can affect this type of classifier by not limiting ourselves to choosing one threshold, but to choosing two. Now, and then the way we do this is we find this threshold, U1, by choosing a false positive rate. Remember, that's what this x-axis is, the false positive rate. So we're going to now select what we want for that, alpha, right? And so we find alpha here, and we run up to the ROC curve, and we find that threshold that gives us that point, and that's U1. And then on this axis, we're going to choose 1 minus beta as 1 minus the false negative rate. Well, 1 minus beta equals 1 minus false negative rate means that the false negative rate is beta. So now you can see how we're getting explicit control over both false positive rate and false negative rate. They're going to be alpha and beta respectively. So up here we find beta, and we slide over to the threshold, to the ROC curve, and we find what U value gave us that point, and it's U0, right? So what we have here now is a way to not just choose one threshold and have no explicit control over false positive rate and false negative rate, because that's, there's two things to control, right? If you're only using one threshold, you can't control both of them. But now if you use two thresholds, you can control both of them. Now, the cost of doing that is that there are going to be patients for which you say, I'm not willing to go out on the limb and make a prediction of C hat equals 1 or C hat equals 0 for. But I don't think that's a bad thing. I think that's progress, right? Because that's recognizing what we don't know and not forcing things just to, make a decision and move on to the next patient, right? We want to be a little bit more careful and personalized with what we say about patients. And we have to understand that the set of features we have to work with, if they're not as effective as we like, that we can always make good decisions. We should understand that we want to try to identify when is it that we aren't confident about our decisions, and then do some extra study of those patients. And I'm talking about patients a lot because I think it's concrete and we can understand medical diagnostics a lot. But of course, not all classification problems are, about that. Sometimes it's should I give this person a loan, right? Yes or no. And then maybe sometimes, well, I'm really not sure. I better dig into some other data to help me decide whether I should give this person a loan. What I normally use for making these decisions isn't quite clear for this person. So I'll recognize that in my classifier. Okay. I wanted to show you now that there are other metrics that come into play, and that would be the probability that we say neutral for a patient, given that they're in class 0, or the probability we say neutral for a patient, given that they're in class 1. These are now new sort of metrics that come into play when we have a neutral zone. And you can, if you draw this picture, so you have your two thresholds, and you go to the left as far as you need to get to where you can then go straight down, then the lengths of these two blue segments, are actually these probabilities. So you can see from a visual standpoint, by choosing these two thresholds, what the fraction of patients are going to be that get classified as neutral. So here again, we can see that the steepness, the bowness of this ROC curve will be very helpful in keeping the length of these line segments shorter. All right, so now let's go to my first of two applications. And this one is classification of prostate cancer patients. So here's a medical example. And we're now considering a patient might have this surgery to remove the prostate. That's called a radical prostatectomy. Sometimes this is done, and if it's successful, it actually eliminates the cancer, right? But if the cancer was a little bit late stage or aggressive, then even when you take the prostate out, that you thought might have had all the cancer in it, and now you took the prostate out. There could have been cancer that maybe had spread to other places, and then it will reoccur. So when we're contemplating removal of prostate, it would be good for the medical team to know if this cancer was the aggressive type. And maybe in that case, the surgery should be complemented with a parallel treatment protocol, such as chemotherapy, for example, or radiation. So you don't want to wait for this cancer to reoccur and then say, yeah, it was the aggressive kind, we have to do more. You want to know at the time you're taking the prostate out that maybe you should do something in parallel to get ahead of, the recurrence, right? So it would be really useful in prostate treatments to be able to tell what type of situation we're in. Is it the aggressive prostate cancer, which generally is a very slow moving cancer, and there's lots of time, to detect and take care of it, but it does depend a lot on the patient, right? So our goal here in this application is to see if a classifier could be used to predict if the cancer is aggressive. And thereby, if we have a useful classifier that does that, we could help the patient decide about having the surgery in parallel with some other sort of treatment protocol. Okay, so here's a training data set that we analyzed. I worked with a urologist at City of Hope Medical Center out here in California, and we had 450 patients that had the prostate surgery, and it was recurrence within 2.5 years of the prostate surgery was the pointer to the fact that that was an aggressive cancer. If there's no recurrence, within 2.5 years, it's probably not going to recur. But if it did recur within 2.5 years, that meant that removing the prostate didn't actually get rid of everything, so that there was some remnants of the cancer left. So that would be recurrence here means the cancer was aggressive, and no means it wasn't. So these are our two classes, right? We had 450 patients, 56 had C = 1 because they had recurrence, and 394 had C = 0. And what we're going to try to do is predict the recurrence as yes or no based on these 4 variables that are correlated to prostate cancer. One is the PSA level, which probably many people get during their many men get during their annual physical exams. And then a biopsy Gleason score is something that's obtained through a biopsy of the prostate. And then these two are lab-based measurements based on blood tests. And the City of Hope researchers were looking at this as a new one. Number 3 here was like a new marker that they were examining at the time I was working with them. So it was bursting onto the scene as maybe some very helpful indicator of the aggressiveness of prostate cancer. So it turned out to be helpful in the model. So we did look at other variables, but these are the 4 that kind of hung around in a logistic regression model as important. And you can see here, this is the fit of the logistic regression, where we have these 4 variables. And I'm just mentioning again here that these 2 are clinical variables and these 2 are lab variables. These are the estimates and the p-values and so on. And here then is the formula that maps these 4 features. So this is that X vector I was talking about earlier, into a single number, T, through this formula. Logistic regression is of course giving us a number between 0 and 1, which is sort of a pseudo probability in a sense, for that class. So then we can put that into the usual sort of traditional 1 threshold classifier. We draw the ROC curve for that, and then we might pick a threshold here that minimizes the overall error rate of the classifier. So, and then here is the confusion matrix for that. So this is not a neutral zone yet. This is just the classifier that might be used if we were just going to force decisions on everybody, right? And you can look here at the off-diagonal elements, as these are the conditional error rates. So if somebody doesn't have a recurrence, I might predict that they do 4.8% of the time. And somebody that did have recurrence, I might say they won't 48.2% of the time. So this is the false positive and this is the false negative. And this is concerning, right? 48.2% false negative is not a useful classifier, even though the overall error rate is 10%. So this underlines once more that you can't just be satisfied with a classifier if you have a low overall error rate, because that's going to be tilted significantly by the imbalance in your data set. You can see that the data set had, if I go back, it was 54 and, oh, sorry, yeah. There was 56 patients in the class 1, but 394 in class 0. So that imbalance leads to the ability to get like a kind of a low overall error rate, but that masks what's happening with these conditional error rates. That's one of the problems we're trying to fix with our neutral zone classifier. So what can we do about that imbalance? We can implement a neutral zone by choosing 2 thresholds. And I'm going to choose these 2 thresholds, the blue points, by trying to match the overall error rate of the previous classifier. So that was 10.2%. The overall error rate is going to be some prior probability of class 0 times the false positive rate plus the prior probability of class 1 times the false negative rate. So I basically have to choose FPR and FNR so that this linear combination of them is 10.2%. And then I want the false negative rate to be, that's the one that's the worst error, right? I don't want that to be equal to false positive rate. I want it to be half of that. So these are 2 equations that give me answers for the false negative rate and the false positive rate, which then lead to these 2 values and tells me what alpha and beta should be, so that I can go to this curve and find my 2 blue points, right? Because alpha is 0.109, I find it down here. I bump up to the ROC curve and I find what U is that value. And beta is 0.054. So 1 minus that is 0.95. So I come on this axis to 0.95 and I slide over here and I get the U0. So now I have my 2 thresholds. And now with those 2 thresholds, I can define my classifier, right? U1, I put in here. So I'm going to compute that logistic regression estimate of probability. And if it's bigger than U1, I'm going to say, I think there's going to be recurrence. So let's do the surgery, but let's also start parallel treatment with this patient. If it's less than the U0 value, I'll say, we're going to do the surgery, but I don't think there's going to be recurrence afterwards. So we don't need to do the chemotherapy in parallel, right? And if it's anything in between, and if you recall, the values here are 179 and 0313. So if that logistic regression probability is bigger than 03 and less than 17, I'm going to say it's too close for me to call. I'm going to put that patient in the neutral zone, and we're going to have to do some follow-up with that one before we know for sure what to recommend, right? And then maybe there's other tests, maybe another biopsy. Maybe you start looking for evidence elsewhere in the body to see if the cancer had spread. So we get a better diagnosis, a personalized diagnosis for that patient. And then just to sum up the comparison, here are the 2 classifiers: single threshold, neutral zone classifier. You can see that they both had the same overall error rate. That was by construction of the neutral zone. That's how I chose alpha and beta to be the case. And then here are the 2 false positive and false negatives. You can see this is half of false positive rate. That's by construction. That's how I chose the alpha and the beta. But look, now you can see much more satisfactory performance with the false negative rate, which is the big problem in this application. Is we're controlling it. We're controlling both of these. And then the cost for that is the probability of neutral zone. So, we are sending 60% of the patients into further follow-up. And it's not always going to be necessarily that high, depending on the application and the features. But I don't think I have to apologize for that. 60% are those are the people that we have to really not just leave it up to math and leave it up to some data science algorithm to say what we should do. Those are the people that we have to be honest and say we don't really know from the math, from the data science algorithm, the best thing for them based on the data we have. And that's progress to have recognized that and to have now put the problem back into the hands of the physicians who can use their human knowledge to decide what's the best thing to do at this point for this patient. Yeah. Okay. So now coming to my last application, which is part of the title of my talk, text mining. I want to show you how we've done neutral zones for 3-class problem, because that example I just gave you was the 2-class situation, which is very common. But 3 classes does arise, and here's an example. And it's around the student evaluations of teaching. We all know about those, right? That at the end of the quarter or semester, we ask our students to fill out forms that tell us how they thought the class went. And there's like a Likert scale set of questions where you strongly agree, feel neutral about, disagree, strongly disagree. And we get summary statistics for those. There's been a lot of discussion around whether those questions are fair and whether there might be some bias with respect to gender and ethnicity of the instructor. There's been complaints about they might measure the so-called performance of the instructor more than like the efficacy of learning outcomes and so on. So a large body of work, and certainly within the University of California system, this is talked about a lot, about like maybe we need to like redesign these questions and try to get away from the what people refer to as the performance aspect of teaching. So I'm going to not comment on that because part of the reason we did this work was to maybe draw some attention to the written comments that students leave. Maybe we could investigate if there were similar concerns about what people say in terms of a written comment. And a lot of times, I know when I look at these student evaluations of teaching, I find the written comments provide a little bit more explanation of what students might have been reacting to. So I'm trying in some ways to put a light on using written comments, but it's hard to do that because we have classes, and many universities do, where there's like 500 students, right? And you could get 40 or 50 pages of written comments easily in such large classes. And really, who's going to be reading them all, right? It's hard to, and then sometimes people will, who are looking at them, will try and summarize for you what they see, and they'll cherry pick, like the comments that support the particular narrative they're trying to make. You don't really have a representative sample of them necessarily if you're reading somebody else's summary. So we set out to develop a machine learning algorithm to classify the written comments. So this is text mining, and label them, as positive comments, negative comments, or mixed. Mixed are the ones that maybe are balanced in their, they say something positive, but they also say something negative, right? So that's the 3 classes: positive, negative, and mixed. And the whole motivation here, or at least a big part of the motivation, is if we can label the comments, we can then group them. And so that when we present them for people to review, we can even have a little table that says, there's 140 positive comments, there's 15 negative comments, and there's 29 mixed comments. And then we show, here's the group of positive ones, here's the group of negative ones, here's the group of mixed. Because then people could sort of in their own minds, sort of create a stratified sample of positive, negative, and mixed. If they don't want to read all 40 pages of comments, they could at least say, okay, I'll read a few of these positive ones, I'll read a few of these negative ones, and a few of these mixed ones, and I'll get some, statistical sampling that's honest about the frequency of these comments. So that's kind of like the idea, to try to bring out more useful use of these written comments, and also along the way, we can also do some studies to see if the percentage of positive comments in the written student evaluations somehow is different for male instructors as it is for female instructors, or faculty of color versus not faculty of color. And that's the kind of comparisons that have been done in the research for those Likert scale questions. Okay, so I think I've talked about this. These are the three comments. These are the maybe I didn't quite say it correctly, because the third category is other, and other is that mixed sort of something positive, something negative that I did mention, but then also other includes like not relevant, because some of the written comments, we've all seen it, right? It's like, they'll just be like, Merry Christmas to you, right? Or, something like, have a great summer, right? So those are not the kinds of questions, the kinds of written comments that tell us anything about would the student recommend the instructor to someone, or would they not recommend not taking, right? That's kind of what the meaning of positive and negative is. So other is, it might be like, the mixed comment might be like, explains things very well, but is a really tough grader, and exams don't cover the material discussed in class, right? So that's like, okay, that's mixed, right? Because there was something positive, something negative, but then have a great summer is not relevant, and that would be other. Yeah. So what we want to do is take this written text and try and come up with this machine algorithm that would identify it as positive, negative, or other. But just like with the medical application, we want to balance the class conditional error rates. So now it's a little bit more complicated, right? Because it's not just false positive and false negative anymore. There's actually going to be 6 of these class conditional error rates, because we have 3 classes, and I'll show you in a moment why there are 6. There was this prior work. Hua Yu was one of my students a little while ago now, who did start to do some work on neutral zones for 3 class problems, but her focus was to control the expected cost of misclassification. Controlling the expected cost of misclassification is a good thing to do if you're able to ascribe costs to errors. But sometimes that is hard to do, right? If going back to the medical case with 2 classes, can I really say like how many dollars it costs me if I tell someone they're sick when they aren't? Well, maybe, because you might be able to figure out like, okay, you told them they were sick. Now they're going to come back and they're going to do some more tests, and that's going to cost this amount of money, and then eventually we're going to figure out that they weren't sick. So you just add up all that money. But then what about the emotional toll of having to go back and do those tests and have anxiety about what's happening? And that's really hard to measure, right? And then about the false negative, like how much does it cost if I tell somebody they're not sick when they are? Oh, well, that's really hard, right? To get your arms around saying, how much does that cost? Because someone might even die, right, from that. So I think it's, yeah, obviously you're going to have to do some sensitivity studies with these costs if you're going to go in that route. Maybe other applications, it's possible to come up with costs of misclassification, but generally that's always hard in decision theoretic kind of context. So what we want to do is try to develop a neutral zone for 3 classes that balances these 6 conditional misclassification rates instead. Those are a little bit easier to intuitively understand. We don't want them to be like 48%, right? We can think about 2% or 5% or something. And if we can control all 6 of those and make them something that we're comfortable with, it's just an easier problem than figuring out like all the conditional misclassification costs. So that's where we're headed. And Dylan Friel is currently a postdoc in my group here at UCR. And then Benjamin Ellis is one of my PhD students at the moment. And this Youngji Lee is a graduate student at Santa Cruz. So we've been all working on this together. Yeah. Okay. So what do we do in a standard 3-class setting? So this is not neutral zone, right? We're going to basically get probabilities somehow or another. And with 2 classes, it was logistic regression. With 3 classes, it could be multinomial logistic regression, right? But there's other ways to get, like you could get from a neural network, or you could get from a classification tree. Any sort of machine learning algorithm could be used to get predicted probabilities, basically, for the 3 classes, P0, P1, P2. And then the way the classifier works is you look for the largest of those 3 predicted probabilities, and you say that's the class. So here's the formula: is if P0 is bigger than P1 and bigger than P2, you're going to say class 0. If P1 is the largest, being bigger than P0 and P2, you say class 1. And then here's a picture in the probability space. So we only have to plot 2 probabilities, P0 and P1. And then they're going to plot in this lower triangular region. And then depending on where that point falls, if it falls up here, it's class 1, here class 0, here class 2. And these are the boundaries where anything in this region is where P2 is the largest. Anything in this region is where P0 is the largest, and so on. Right? So this would be the classical sort of way to handle a 3-class classification problem. No neutral zone. Okay. But we want to add neutral zone because just for the same reason we put it into a 2-class problem. There could be a reason and that you don't want to force a decision into any of these 3 classes. So one approach could be to choose a single value of L and insist that not only is P0 bigger than P1 and P0 bigger than P2, but it be bigger by this amount of margin L, so that I could control it, right? I could say, I don't want it just to be bigger because there could be a lot of borderline cases. You know, I'm going to say it has to be bigger by at least this much than both of those. And then here's the same thing for saying class 1 and then class 2. So, and then we could determine L, this is a typo here. This is what we could do, but that's not what we're going to do. We're not going to get into cost of misclassification. We're going to take L and try to control the misclassification rates of this classifier. Okay, so there's 6 of them. There's the probability I say 0 when it's really 1. There's the probability I say 0 when it's really 2. There's 2, right? And then there's the probability I say 1 when it's really 0, or a probability I say 1 when it's really 2, and there's 2 more. So there's like 6 of them. And I'm going to choose L so that all 6 of these reach a worst case value. So maybe like 0.1, right? I want all 6 of these to be 0.1. So if I start L equals to 0 and I increase gradually, all 6 of these conditional misclassification rates are going to 0. So I'll be able to find an L that make them all less than, say, 0.1, right? And some will be way less than 0.1, but they'll all be less than 0.1. And it would give me sort of a uniform upper bound on all of the 6 conditional misclassification rates. And the way this looks is this picture. The dashed lines are what you've seen before, which is like the traditional sort of no neutral zone classifier at all. But then these lines here, the black solid lines, push away from the dashed lines to create this inner region, which is all the neutral zone. So now I again plot P0, P1, but I only say class 2 if I'm here, whereas before I was saying if I was all here. Now I only say if it's here, and likewise for class 0 and class 1. And if I'm in this inner region, then that's the neutral zone. That's when I say I don't really know, right? Okay, so that's what we call the symmetric neutral zone, because all of these, this distance here is the same as that distance here, and so on. Another way to do it, though, and a better way, is to use an asymmetric neutral zone classifier. Rather than choosing a single L, we choose 6 L's, right? Because now we're going to, if you look at this formula, we're going to say class 0 for if one of these two things happens. First, we look and say, okay, P1 is bigger than P2, so that rules out P2. And then we're going to say P0 has to be bigger than P1 by this margin. Or it could be that P2 is bigger than P1, so that rules out P1. But then we want P0 to be bigger than P2 by this margin. So we get a little bit more precision now over by how much we want the victor to win, right? Because these 6 constants, L01, L02, and then there's 4 more, that's basically setting the margin by which the highest one has to win the race, right? And now our chore is to find these 6 L's, and we approach it the same way. We do a grid search over all the L's, where we make all 6 of these conditional probabilities less than some target, right? And when we do that, you'll get this interesting plot over here, where now you don't see the same distances between the dashed lines and the neutral zone, but it works the same way. We're going to say class 2 if our point falls now in here, and class 0 if it falls in here, and 1 up here. But now our neutral zone is asymmetric around the dashed line, and the benefit of that is we now can get tighter control over all 6 of these conditional error rates. I'm just going to skip this slide to move a little faster. Okay, so what's the impact of adding these neutral zones? Both the symmetric and asymmetric neutral zones, they're always going to give us the same predicted class as not using a neutral zone, or they'll change that predicted class to neutral. So we don't introduce any new errors. We're not going to cause somebody to be a class 1 that's really a class 0 if the original no neutral zone classifier didn't do that. We're just going to change some of the no neutral zone classifications to neutral, because we're going to recognize that that classification is sketchy, because there's not enough margin in the predicted probability. It's too close to the second place winner, right? We're trying to basically make sure that all of the largest probabilities are sufficiently far away from the second and third place finisher before we actually make a decision. Otherwise, we're going to say neutral. And by doing that, we're going to achieve better balance in these 6 conditional classification rates. And now my example will show you how that works for our data set. So I think I'm going to skip this one too, although that's a pretty plot, but I want to pay attention to the schedule. All right, so coming back now to our data application, I'm looking at these written comments, and I have 104,000 from University of California, Santa Cruz, and 35,000 or so from my campus, Riverside. These were labeled by undergraduate students to get the true labels, and we had majority voting in case that there was a difference of opinion. We had 3 undergraduate students reading the comments and coming up with a consensus on, are these positive, negative, or other? So that's how we got our true labels. And you can see here that the campuses aren't that different in terms of the percentages, but there's maybe a little difference. Okay, so that's our data set. And here's the key part. Now we have to figure out how to get features from a written comment. And we're going to use something called word to vec. And the primary goal of word to vec this is a machine algorithm that it's going to try to predict what word is in the middle of a phrase based on the words that are not in the middle. That's like what word2vec primary purpose is. You know, I have a 5-word phrase, and I'm going to try to predict what word is number 3 from what I know is first, second, fourth, fifth. That isn't really what I want to do with word2vec, but there's a byproduct of word2vec that is perfect for what I want to do. Because if the byproduct is a matrix where all the words in a dictionary are mapped to a vector of numerical features, and you choose how long you want this vector to be. A sort of a default value is 40. So I can use this word2vec algorithm to say for every word, like, you know, textbook, right? That turns the word textbook into a 40x1 vector of numerical features. And classroom notes, right? There's classroom and there's notes. Each of those 2 words, classroom and notes, is turned into a vector of 40 numerical features by this word2vec algorithm, which is the underlying machine algorithm is a neural network. So I don't really want to predict words. I just want to extract information about the words in a numerical vector space. And so a byproduct of word2vec is a matrix that does just that. Every word in the corpus is represented now by a vector of numerical features. So what I do to get my comment numericalized is I just take every word in the comment, I go find the row in the matrix for that word, I extract it, and then if there's like 60 words in the comment, I have 60 rows that I pulled out, and then I average those rows. Basically, it's a little bit more of a normalization / average, but for today, let's call it an average. So I take those 60 rows and I average them to get 1 row, and that's my set of numerical features for the comment. There's a lot going on here, but that's the gist of it, right? Because that might have been a puzzle in your mind, like how are you going to take a 60-word comment of words and get a vector of numerical features? This is how we do it with this word2vec sort of software technology. Once we have that, we're doing multinomial logistic regression, because now we have our numerical features for each comment. We have the label that the students assigned, and we're going to take 80% of our data set as the training data, and we'll use 20% as test set. So with 3 classes, we have 2 logits, and we get maximum likelihood estimates. And now here's how we get our 3 probabilities for a new comment that comes to us in the test set. We go through this word2vec feature extraction. We get 3 estimates, P0, P1, P2, and then we plot them into that space that we were talking about. And now, so now let's see how it works with the data. So here's the Santa Cruz campus, and this is the traditional multinomial logistic classifier, no neutral zone. And if you look at these 6 bold numbers, those are the conditional misclassification error rates. And there's a lot of variability in them, right? There's as small as 0.05 and as big as 0.28. So that we're not really controlling them. Overall error rate is 21%, maybe not so bad, but then we might be uncomfortable with having the 6 conditional misclassification error rates being variable. So now we implement this asymmetric neutral zone classifier, and we're going to now insist that all 6 of these be less than or equal to 10%. And you can see that we've achieved that. And we've lowered the overall error rate to 11%, right? It was previously 21%. So now we have smaller error rate, better control over the conditional error rates, the bold numbers. And the cost of that is we're putting 23% of the comments into the neutral zone, where we would say we don't really have enough confidence to say positive, negative, or other. So we're just going to say, you know, we'll put that as neutral. Yeah. Okay. And then here's a plot of, I don't really need to go into this too much, but in case you wanted to see the asymmetric neutral zone, that everything that's falling in this region here is neutral. And so this would be all your class 1, this would be all your class 0, and then class 2. That's just a diagram using the test data set. That's 20% of our data. Yeah. And then for UCR, this is the data set for no neutral zone. We have these variability is pretty high on the 6 conditional misclassification rates, 40% all the way down to 4%, and an overall error rate of 22%. If we add the neutral zone, now we can see we're controlling all the bold numbers, and we're getting a smaller error rate, cutting it in half almost to 10%, and now 30% of the comments are being placed into the neutral zone. That's the exchange we're making. Yeah. Okay, so wrapping up, yeah, this is just a picture of the neutral zone for UCR. There's an advantage to, I think, having these labels on the written comments that we can group them and help people read and digest the full impact of all of them. And the asymmetric neutral zone is the one we recommend over the symmetric one because it actually gives you better control over the 6 conditional misclassification rates. You notice there was a little bit of a difference in the number of comments that go into the neutral zone between the 2 campuses. That's because the 2 campuses ask for open-ended questions slightly differently. Riverside just asks for one, like, is there anything else you would like to add about this course? Whereas in Santa Cruz, they asked that with 3 different sort of targeted questions to certain areas. So campuses do these things differently, and we're not proposing that we fit one model from our data that would apply to all universities. Instead, we would advocate for using this methodology and fitting it to your own campus, individually. So in sum, the overall misclassification rate we've discussed can really mask underlying weaknesses. You've got to pay attention to these conditional misclassification rates, and neutral zones is a good way to do that. But we do have to recognize when you put something into a neutral zone, you have to do something with it sometimes, right? In medical situation, you can't just leave the patient in the neutral zone. You have to go and do something to come up with a decision ultimately. In my text mining example, I don't think I have to do anything, right? I can just put these comments that are neutral into a neutral zone bucket. I'm not going to try and parse it anymore to try to figure out, is that really, could I do something else to figure out if that is that positive, negative, or other, just leave them in the neutral zone. Yeah. Yeah, so the overall misclassification rate is always going to be better if you use a neutral zone, and you're going to have tighter control with your conditional misclassification rates. Okay, I think that's what I wanted to share today. So I'll stop there. Thank you.
Thank you very much, Dan, for an excellent talk. So developing evaluation metrics for classifiers are hard and not straightforward. And your example of the text mining are so relevant to all of us who are on the journey of getting tenure and promotion. I look forward to try the neutral zone classifier on some of the problems I have at hand.
All right.
Any questions from the audience? There was one, but the asker has to leave. I'm going to ask the question for him or for him. I'm curious, you develop your method starting off with a 2-class classifier, but if I see correctly, you introduce with the neutral zone a 3rd class. Do you arrive at the same method if you start off with 3 classes in the first place? Also, if you use a 2-class classifier that quantifies uncertainty of the classification and accept the decision classification only if the uncertainty is acceptable, do you get a similar method? I think your talk answered a part of his question already.
Yeah, so if the thought was that you could say that a patient was sick or they weren't in your training data. If you had labels that said the patient is sick, I'll say diseased. The patient is diseased, non-diseased, or I don't know. I don't know, like that's typical of what we would expect in an application, right? For medical diagnosis. I mean, the true label is probably going to be like diseased or non-diseased in some way or another, because the patient is going to have some kind of symptoms, and then our goal is to just correlate that status, disease, non-disease, to some features that will help us. So I don't think that all applications would amend themselves to saying that I don't know is a true label. I think that was the question. It's like, could I just make I don't know a true label? I mean, maybe there's something to think about there, because there is semi-supervised learning where you try to bring in data that doesn't have any label at all. That's not quite the same thing as saying I do have a label and it's I don't know, right? So I don't think it's the same. So my answer to the question is I don't think it is the same. I'm not sure if all applications would amend themselves to saying I don't know is a true label, but it's a good question, and maybe I should think about it some more.
All right, thank you. Thanks, Dan. If there are no other questions, we're going to have a break, and we're going to resume after the break at 3 p.m. for the short course on scientific writing.
Okay, all right, thank you, everyone.
Thank you.
Let me add my thanks, Dan, to your wonderful presentation. It's
Thanks,
great.
Tim. It's good to see you.
Yep, good to have you with us.
Thanks.
And I will put Don Richards' information up on the screen, and you can all take a break and come back at noon Pacific time and 3 o'clock Eastern time.